Okay. So, what we have done in the last lecture was outlining the way to go to derive the parameters of Stokes starting from the equations of motions. There is a different route to achieve the same by considering the direct product of the solutions and generating a 2 by 2 matrix that goes by the name coherency matrix. So, in this approach, the 2 degrees of freedom's ensemble average is taken. The variation, that means, we just look at the time variation from the observational people's point of view, either collect the variation of a particular variable over various wavelengths and then average over it. So, most of the objects those emit radiation are not in the are not pure or line spectra, or take a time average. So, if we do that, we get what we have written in equation 1. The coherency matrix is the intensity in the parallel direction as the first element. There is a cross correlation between the parallel and perpendicular direction in the off diagonal elements and the intensity in the perpendicular direction of the 2 waves. So, if we decide to define the intensities I by the first line of equation 3, the difference in the intensities of the parallel and the perpendicular direction by another variable q, the real part of the cross correlation related to something called u and the imaginary part by another quantity v, then the coherency matrix can be recast in the form of equation number 4. So, if we take the trace of the coherency matrix, we get the intensity, and similarly we can find out from each element of the coherency matrix the corresponding quantities q, u and v. Under this transformation of coordinate rotation, the original variables, that is parallel and the perpendicular ones, go over from parallel and perpendicular to the rotation matrix multiplied by the column vector that is describing the parallel and the perpendicular components. So, if that is the situation, then the direct product under this rotation of the coordinate actually takes the following form, that is given by equation 5, that is rho goes to rho prime, which is the rotation matrix times the coherency matrix in the unrotated frame times R inverse or rotation matrix inverse. And the upshot of this whole exercise is the rotation by an angle alpha of the observer or the emitter can be described by the following changes in the respective variables of q, u and v, that shows that only q and u, they take part in this rotational transformation and the other two remains invariant. So, what are the other two variables? Those remain invariant. One of them is easy to understand, that is the intensity. So, intensity of course remains invariant, and the Stokes variables V, that also remains invariant, and how they are related to each other is given by equation number 7. In general, q and u are used to describe the degree of linear polarization and V is circular polarization. So, the effect of rotation is, you can guess on what are the sectors on which it is going to be affecting and the ones those are not. So, coming back to the issue that we started with, that under a Lorentz transformation that has generators of boost and generators of rotational symmetry and the boost symmetry. So, under rotation it is the variable q and u of Stokes, those undergo a transformation. However, the other two variables, intensity and circular polarization measure, remains unaltered. So, this is in addition to the medium effects that we have discussed during the course of these lectures. So, with this I would like to stop here today. Thank you.